Hey there, it's week 8. We're working on chapter 4, part 2. And last week's lecture ended with molecular equations, complete ionic equations, and net ionic equations. And what we're going to begin with this week is we're going to begin with precipitation stoichiometry. So let me just go over real quick what we're going to be doing today. First, we're going to do precipitation stoichiometry. All right, and after we do precipitation stoichiometry, we're going to be looking at acid-base reactions. And then we're going to be working on redox reactions or oxidation reduction. Okay. All right, so let's go ahead and begin. And we're going to work on a problem that I'm actually taking directly out of the slides. And just to remind you that you should have your periodic table and your ion list every time you're working in this chapter. So you should, if you don't have those things, I would pause the video and go get them, as well as getting your calculator. Every time I calculate something on here, you should pause the video and you should calculate it as well, because knowing that you're getting the same answer I'm getting will make this whole process a lot easier. Okay. So first of all, in this problem, it tells us that we have, and I'm going to paraphrase it a little bit, but we have 10 mils of a 0.3 molar sodium phosphate solution. So when it says sodium phosphate, I know that I'm just going to keep track over here. That's Na plus and PO4 3 minus, which means that I am Na3PO4, and it tells me that I have a solution, which means that it is aqueous. Okay, and then it tells me that I have 20 milliliters of a 0.2 molar, and this is a lead 2 nitrate solution. So again, keeping track, lead 2 and nitrate. Okay, and I'm just tossing them up there because I have this one pretty much memorized, but you would of course need to be looking from here. Okay, and so this means that we have PbNO3 2, and that is also aqueous. Okay, and they basically want to know what's going to happen. So let's work through this. The first question is, what precipitate will form? Okay, so I had an ulterior motive for listing all of the ions over here, and that's because now we can take a look at this. Okay, so we know that lead 2 nitrate is aqueous because it tells us it's a solution, and we know that sodium phosphate is aqueous because it tells us it's a solution. Also, we can see that we have the sodium and the nitrate, and if you remember from last week, we know that those ions are always ions for solubility. So now what we're going to do is we're going to look at what we have left over, and here I have a lead 2 and a phosphate, and if I check my rules, I know that lead 2 phosphate would be a precipitate. So then I can write that down here, Pb3 PO4, and it's going to need to be a 2, so I have to put it in parentheses, and that's going to be a solid. And then because this is a molecular equation, I will just go ahead and write that NaNO3 aqueous. My spectator ions are still in solution, and I just write them as aqueous because. Okay, so now before I can go further, I always need a balanced chemical equation. Okay, so that means that I have to balance this before I can do anything else. And the way I do it is I look at my solid here, and I see that I have 3 lead units. So I can just put a 3 in front of my lead compound in my reactants. And then I look at my phosphate and I see that I have 2 phosphate units. So I can just put a 2 in front of my phosphate compound. Now I know that my precipitate is balanced. So I see 2 times 3 is 6 sodiums and 3 times 2 is 6 nitrates. So all I have to do is put a 6 here. And I'm gonna go ahead and put a 1 in front of my lead 2 phosphate just because it's gonna help me see that for my molar ratios later. Okay, so that's the setup for this. Now the next part of the question says, how much of my lead phosphate will I make? And since it's a solid, that how much is going to be in grams. Okay, so my setup is complete. I know what I'm looking for. So let's take a look now. My step 1, and I'll go ahead and write that over here. Step 1 is going to be, see how we have quantities, if you can hear the noise in the background, it's my dog, and she's working very, very, very hard to kill a squeaky squirrel. All right. So you see how we have quantities for both of our reactants? Okay, well, what that means is that this is a limiting reactant problem. And so we need to decide which one is our limiting reactant first. All right, so this is the way I'm going to do this. There are other ways of doing it. Make sure you show your work so that I know that you followed some kind of step-by-step method. Okay, so step 1, regardless of what method you use, is going to be to find the number of moles of each reactant. Okay, well, what I need to do, because now remember that moles is equal to my molarity times my volume in liters. So that means that I need to change this 10 mils to 0.0100 liters. And I need to change this 20 mils to 0.0200 liters. Now I can find my number of moles using this equation that I have right here. Okay, so the number of moles then is going to be my molarity, 0.03, and I know why I have my significant figures, so I'll leave it off for now, times my volume in liters, 0.01. Okay. Looking at that, I transposed these, 0.3, there we go. Okay, so 0.3 times 0.01 is 0.003 moles. Okay, now I can do the same thing for my lead 2 nitrate. Okay, and I say, okay, well, I have 0.2 for my molarity times 0.02 for my volume, and that gives me 0.004 moles. Okay, now there's 2 ways to do this, okay? The first way is you can compare these 2 mole ratio quantities to the moles we have and determine your limiting reactant. I'm going to use the other method that we have, and that is where we just do our stoichiometry twice and pick our lower value. Okay, so in this case, I can now my step, let's see here, I'll go with green. My step 3 is going to be stoichiometry starting with moles. So until now, we've always done our stoichiometry starting with a mass. But we don't need to start with a mass, because that first step, you start with a mass and you put in a molar mass in order to get to moles. But because we started with an aqueous solution, we didn't do that first step. We don't need to do the first step. So you do not need the molar mass for your reactants in this kind of a problem. So we take our first one here, that's 0.003 moles of sodium phosphate, times, now the next thing that I'm going to have here is my mole ratio, and that's 2 moles of sodium phosphate to 1 mole of my product. That's Pb3PO4 2. And now the next thing that I'll need is my molar mass of my unknown. Okay, 1 mole Pb3PO4 2, and I have actually calculated that value ahead of time. Okay, and it is 811.54 grams of Pb3PO4 2. It's a big one. There. All right. So the value that we get for this is going to be 0.003 times 811.54 divided by 2. And I can have only 2 significant figures because of the way my slides are written. I might have actually updated the slides so that I have 3 significant figures though. So actually what I want to do is I kind of want, you wouldn't be able to do this, but I want 3 significant figures here. So I'm going to go ahead and alter this problem. Okay. And so if I have 3 significant figures, this gets 1.22 grams of our lead phosphate. So now I'm going to do this problem a second time with the lead nitrate, the lead 2 nitrate. And I have 0.004 moles of my PbNO3 2. And again, I do not need a mole ratio, I do not need a molar mass for my reactants because I already have calculated the number of moles. And all the molar mass for the reactant does is go from grams to moles. So here I'll put in 3 moles of PbNO3 2 to 1 mole. Actually, I'm going to change my color here so that you can see that what this is now from here, it's exactly the same. 1 mole Pb3PO4 2 times, and then still the molar mass, 811.54 grams. So this method, it's mostly the same. Again, if you can tell by looking at it, and some people are good enough at math in their head that they can, okay, which one your limiting reactant is, then you don't have to do it twice, but you better be right. Okay, and now when I work my way through this one, I get 0.004 times 811.54 divided by 3. And if I can have 3 significant figures, I get 1.08, excuse me, grams of my lead phosphate. Okay, so now remember, when we're using this method for limiting reactant stoichiometry, our answer is always the smaller quantity because each one of these represents the maximum that can be made with our amounts. Okay, so what that means is that this one is my limiting reactant. And this here is my final answer. Okay. And that's basically a very long, thorough problem for precipitation reaction stoichiometry. All right, moving on to our next topic. Our next topic was acid-base chemistry. All right. So again, you can read the slides for some of the definitions, but let's start by looking at the idea of what an acid-base reaction might look like. So here's the most simple one, hydrochloric acid and sodium hydroxide. And this is one of the easiest ones to do in the lab because you have a very strong acid and a very strong base, and they're very simple. It's all 1-to-1. Okay, so what do I mean by that? Well, hydrochloric acid, remember hydro means no oxygen. So chloric must come from chloride, that's Cl minus, and an H plus, and these are 1-to-1 balanced. So we just have HCl, and it's a strong acid, so it's going to be 100% aqueous. And then we have sodium hydroxide, Na plus and OH minus. So that's going to be NaOH, and that will also be aqueous. Whenever we have an acid-base reaction, what's going on here is that our proton and our hydroxide combine to form water. So we're always creating H2O liquid as our product in an acid-base neutralization reaction. And then whatever is left over is going to be the salt or the ionic compound that's left from the acid and base ions. And in this case, that is just NaCl, and we know that sodium chloride is aqueous from our solubility rules. So this is very standard because we just have one proton and one hydroxide, and they balance evenly. Let's take a look at what would happen if we had a different reaction. Instead of hydrochloric acid, let's do sulfuric acid. And sodium hydroxide. Okay, sulfuric acid and sodium hydroxide. And so we'll come out here and we'll say, okay, well, our sodium hydroxide, we already know that that's an NaOH aqueous because we used it in our last reaction. Now let's look at the sulfuric acid. There's no hydro here, so sulfuric comes from 8. So the sulfate anion is SO4 2 minus. If you don't remember how to do that, I strongly suggest going back to chapter 2 for just a few minutes and reviewing how to make these acid and ionic compounds. It's going to be really important. And acid again means H plus out front. Now we're going to need 2 hydrogens to balance out that 2 minus charge. So this becomes H2SO4. And sulfuric acid is a strong acid, so it is aqueous. Okay, now let's take a look at what's going on here. Here we have 1 hydroxide, but we have 2 protons. Okay, well that means that with those 2 protons, we'll need 2 hydroxides to balance out the 2 protons. 2 protons and 2 hydroxides make 2 waters, 2 H2O. And that's how you're going to determine how you're going to balance an acid-base reaction chemistry. Okay, so here we have, and then we take what's left over, and that's the sulfate plus the sodium. We'll kind of identify those there. And we know that we need 2 Na plus to balance out that 2 minus charge. So this becomes Na2SO4. We know from our solubility rules that sodiums are always soluble, and so this becomes aqueous. Okay, so these are some examples of balanced acid-base reactions. Let's take a look now at a problem that looks at the concept of a titration. Now what a titration does is a titration takes a quantity in like a small beaker or an Erlenmeyer flask and another quantity in a burette. And it's how you can determine concentration for an unknown acid. If you were in the lab, you would definitely be doing a titration. So it's a little bit disappointing that you're not. But the lab that you should have done last week for this chapter will have looked at some of the reactions that we're doing now. Okay, so let's take a look at that sulfuric acid sodium hydroxide problem from before. And we had H2SO4 aqueous plus 2 NaOH aqueous, yielding 2 water liquid plus Na2SO4 aqueous. And it's all balanced. We have 1, 2, 2, 1, if we want to put them in like that. Now let's take a look at the problem in the slides, just so that you can see how it's done. And it tells us that for a titration of sulfuric acid with sodium hydroxide, how many milliliters of a 0.7 molar NaOH, so let me just pause and write that in, would be required to react with 45.2 milliliters of a 0.5 molar solution. Okay, that's the problem in the slides, except that I've done that one in the slides for you. So let's actually adjust this a little bit. Let's turn it around. And let's say that instead that we have 15.2 milliliters of a 1.23 molar sodium hydroxide solution. Okay, and we want to know what the molarity of our H2SO4 is if we have 17.8 milliliters that's neutralized by this. So what happens, what we're looking at here is we're saying that we take 17.8 milliliters of H2SO4 and 15.2 milliliters of our 1.23 molar sodium hydroxide, and then we get 100% water out of the deal. And all of our H2SO4 and all of our sodium hydroxide is neutralized. And so we want to know then, well, what was the concentration of that sample of H2SO4? Okay, well, what we're going to use for this is we're going to use the dilution equation. Okay, I'm hoping you remember that. It was M1 V1 equal to M2 V2. And what we want to do is we want to say, okay, well, let's identify our M1 V1. Let's identify solution number 1 as our acid, and the M2 V2 solution number 2 as our sodium hydroxide. Okay, now what we need to do is we need to determine what each one of these is going to be. So for our acid, the volume is 17.8 milliliters. Okay, and we have this H2. We're gonna look at that later. The thing to remember here is that we're looking here for the molarity of our H plus, okay? And that's gonna be important when we talk about ion concentration, and we did that at the beginning of last week. Okay, so now let's take a look at our M2 V2, and you'll see here that we actually don't need to use these mole ratio numbers. All right, so we take a look at our base, and our base is 15.2 milliliters, and that's our V2. And our molarity is, because we only have one hydroxide, okay, and I'll actually write that down. One hydroxide means that M2 equals the molarity of our sodium hydroxide. If we had like a calcium hydroxide that has 2 hydroxides, then that would change the molarity of our hydroxide, because M2 isn't the molarity of our sodium hydroxide, it's the molarity of OH minus ions. And M1 is not the molarity of our H2SO4, it is the molarity of our H plus ions. And that, we'll come back to that in a minute. Okay, so that means that 1.23 molar is our M2 value. Okay, so now we can set this equation up, and we have M1, which we are looking for, and we have 17.8 milliliters. And then we have our M2 here, 1.23, times our V2, our volume of our base, which is 15.2 milliliters. And now we solve for M1. And that's 1.23 times 1.23 times 15.2 divided by 17.8. And that tells me that my M1 value is 1.05 molar. Okay, so if we had a monoprotic acid, so an acid like HCl that only has one H plus in it, then our M1 is going to equal the molarity of our acid. But remember, this is the molarity of H plus ions. And so let me show you then how this would work. If we have 1.05 molar H plus ions, and we have 2 H plus ions for every 1 H2SO4, then we find 1.05 divided by 2 gets us 0.525 molarity for H2SO4. And this is a problem, it's similar to the one in the slides, but it's actually backwards for the problem in the slides. So again, remember that these lectures are only meant to supplement the slides and the annotations. So make sure that you look over the slides and annotations very carefully. Okay? All right, so we are ready now to begin our study of oxidation reduction reactions. Now, oxidation reduction reactions are all about transfer of electrons. And I'm not going to painstakingly list the rules for oxidation states. If you do not have already taken notes on the slides and the annotations, I want you to stop this video right where you are, and I want you to go take notes on oxidation states and then come back, okay? So now I'm assuming that you have your oxidation states handy, and we're going to look at how to apply those. Okay, so first of all, I'm going to put up some problems, and we're going to work through them. Let's look at CO2, and again, I'm going to put here oxidation states so that it's very clear what we're working on. Let's look at CO2. Let's look at some parts of our chlorine series. Let's look at HClO, okay, the hypochlorous acid, and then let's look at HClO2, chloric acid, okay? And then let's go ahead and look at, we'll say fluorine gas, and that works. This should cover what we need. All right, now let's look at the easiest one first. The easiest one first is this fluorine. And the reason that that's the easiest one is because this is fluorine gas in its natural state. And the first of our rules is basically an atom in an element or in its elemental state is always 0. So this fluorine is going to be 0. Okay, just for the sake of argument later, let's show chlorine gas, Cl2, and its oxidation state is also 0 because it's in its elemental state. Okay, now let's come over here and look at what we have. Well, we have a rule for oxygen in almost every form, unless of course it's by itself. In this case, carbon dioxide, the oxygen will have an oxidation state of -2. Okay, there are 2 of them. So 2 times -2 means that we have an overall contribution of -4. And I always hesitate to put this -4 up there because this -4 is not your answer. Unfortunately, if you give me -4 as your answer, I will mark it as wrong. You have to list oxidation states as only existing on one atom, one. Okay, it cannot be on both of them together because we look at transfer of electrons per atom, not per quantity of elements. It's for each individual atom. So you have to list oxidation states like this. Now, but it's easier to keep track of them when we see what our contribution is. If the oxygen contribution is -4, then the carbon contribution has to be +4. Okay, now in this case, there's only one of them. So in order to balance out the -2s on the oxygen, we need a +4 for our carbon oxidation number. Okay, now let's look at HClO, the hypochlorous acid. First of all, H is actually H+. So let's take just a minute and separate these. Here we have H+ and ClO-. And sometimes that will help a little bit because one of our rules is that an ion adds for the ion. So because this is H+, we know that the oxidation state for it is +1. This oxygen, again, is -2. Peroxides are rare. If you have a peroxide, it's -1, but the rest of the time, oxygen's -2. Okay, now what we need to do is we need to reserve out this -1 charge. Okay, and so that means that the chlorine has to be a +1 for this all to balance. Okay, and so +1 -2, those balance for an overall 1- charge, and the whole thing together, +1 +1 -2, balances for an entire HClO as balanced, as neutral. All right, so now let's look at, so this was our hypochlorous acid because HClO1- is the hypochlorite ion. Now ClO2, that's H+, and ClO2-, and ClO2- is the chlorite ion, not hypochlorite, but chlorite, which means that this becomes chlorous acid. Okay. And so the oxidation state on our hydrogen is still, whoops, I was saying hydrogen, and that's what I wrote, is still +1, and the oxidation state on my oxygen is still -2. But now there's 2 of them, right? Okay, so that means that we have an overall -4 contribution from it. And so because we have that 1- charge here that we have to balance out, that means that the chlorine has to be +3 to balance out the -4 and still have 1- left over, which means that that's +3. And then you can also think about it as +1 +3 is +4, and 2 - 2s is -4, and that is balanced. So that's just kind of a refresher on balancing these. All right, so now let's take a look at oxidation reduction in total. Okay, so what we're doing now, they've actually changed it and gone back to a more complicated version of balancing oxidation reduction reactions in the 10th edition, which is what your OWL is based on. However, I'm not changing my curriculum between last semester and this semester. Okay, so let's look at a simplified version of oxidation and reduction. Oxidation is a loss of electrons, and reduction is a gain of electrons. Okay, I like the mnemonic Leo, Gur. Leo, the lion, says Gur. And that's loss of electrons is oxidation, gain of electrons is reduction. And that's just kind of the mnemonic to remember what's going on here. Okay, so then let's take a look at an equation and let's balance it using the redox method. Okay, so let's look at zinc, metal, plus hydrochloric acid, aqueous, yielding zinc chloride, aqueous, plus hydrogen gas. Okay, and this is one of the reactions that you probably saw in the lab for this section, and this is oxidation reduction. Okay, so now we take a look here, and before we balance it, remember we balanced the acid-base stuff a little bit differently so that we could see the actual chemistry involved. Okay, so we're going to do the same thing here, and what we're going to do is we're going to start by assigning oxidation states. This is zinc metal all by itself, so its oxidation state is a 0. Now we have HCl. Well, this is H plus and Cl minus, which means that the oxidations for this are +1, -1. Now we have zinc 2 chloride. And so because that means that our chlorides are still -1, there's 2 of them, it's zinc 2, so the oxidation state on my zinc is now +2. This is hydrogen gas all by itself in its elemental form, which means that it's going to have an oxidation state of 0. Okay, so now let's take a look at what happens now. What we see is, let's take a look at our tie lines. And tie lines are the lines that demonstrate to me that you know what's moving. So in your test for chapter 4, you either have to write this out and email it to me, a handwritten example, and email it to me on paper, or you have to describe what the tie lines look like in Brightspace. So here we have the zinc, and that is going from 0 to +2. And you can see that you cannot do these correctly without having those oxidation states correct. So really spend time looking at those. If we went from 0 to -2, what this means, +2, sorry. If we went from 0 to +2, we lost 2 electrons. Lost electrons means oxidation. So our zinc was oxidized. The substance oxidized is also the reducing agent. So the thing that is oxidized is the thing doing the reducing. All right, now we look for the other place where we can see a change, and we see that our hydrogen goes from +1 to 0. +1 to 0 means that we gained 1 electron. Okay, if we gained 1 electron, that's reduction. So that means that hydrogen is was reduced. And hydrochloric acid is our oxidizing agent. Okay, now we go back through here, and you might not see why it's important now, but it would be important if we were doing a difficult oxidation reduction balancing, which involved acids and bases in a different way. But so we're going to work through the process now. Here you can see that each zinc loses 2 electrons, but each hydrogen only gains 1 electron. So we need this 1 to equal 2. And that's why we know that we need a 2 here. And then we can check. Okay, well, 1 zinc, 1 zinc, 2 chlorines, 2 chlorines, 2 hydrogens, 2 hydrogens. Okay, and that is a complete balanced oxidation reduction. Let's look at another one. Actually here, hang on. I want to move this down a little bit. Copper chloride aqueous yields copper 2. Oops. Okay, so copper 1 chloride aqueous yields copper 2 chloride, CuCl2, also aqueous and solid copper. Okay, now let's take a look at this. This one's a little bit harder to see. So it's a good one to do. See how we have the CuCl2 and a copper. So we have 2 coppers and 2 chlorines. We need 2 coppers and 2 chlorines. I could put one here, but I'm going to actually redraw this like so. Okay, and why is going to make sense in a minute. This might be a little different how I did it in the slides, but this is a good way to see it. Now that I've done that, in this case, I've sort of balanced it preliminary ahead of time. Copper 1 chloride means this is +1 -1 and +1 -1. Now we have copper 2 chloride, so this is +2 -1. And this is copper metal, copper solid, which means that it's in its elemental form, so its oxidation state is 0. All right, now let's take a look at what's going on here. First, let's find where we're oxidized. We can see here, this copper chloride goes from +1 to +2. And so if we go from +1 to +2, we're losing electrons. So this copper lost 1 electron, and that means that it was oxidized. And this compound here would be called the reducing agent. Okay, now let's take a look at this copper. We can say that this copper, and it's arbitrary which one I picked, goes from +1 to 0. That means this copper gained 1 electron. And so this copper was reduced. And this copper chloride compound is our oxidizing agent. And this is just to show you that sometimes you can have something kind of weird going on where you have copper being oxidized and reduced at the same time. If you wanted to, then at the end, you could rewrite this as 2 copper chloride aqueous, copper 1 chloride, yielding copper 2 chloride and copper metal. But it's not necessary. You could leave it in this first step as well. Okay, that was the end of chapter 4. I will do a lot more problems and some very difficult ones with you guys in recitation. So I'll see you there. Bye.